Remember, binary digits can only be 0 or 1. There are no fractions. There is no halfway. They can't take on any value they want to take. This quality is called being discrete. Also recall that anything binary is digital, and anything digital is binary. What's the alternative to being digital or binary? It's called being continuous. So continuous variables can take on any value. 1, 1.2, pi, 1/3, whatever. If you're measuring a continuous quality, we usually call that an analog measurement. Let's discuss an example. Speed. The speed of your car is a continuous variable. It can be any number at any time. Usually your speedometer is analog. It's usually a needle along a dial. You could do a digital speedometer though, and that would be a little bit different. Well, how would it be different? Speed is continuous in two ways. Continuous across time. You can be any speed at any time, and sometimes an analog speedometer could show you that better. And speed is also continuous along quantity. You can be any number of speed. You can be 20, 20.1, etc. Well, your digital speedometer wouldn't work like that. Your digital speedometer has to update at set times. It couldn't update at an infinitely small time. So it's discrete across time. And your digital speedometer is also discrete across quantity. It can be 20, it can be 21, but it can't be every fraction in between. This is analogous to ultrasound, where our transducer can give us any voltage. It's a continuous variable, and that voltage is an analog signal. We need to digitize it, and when we need to digitize it, we do that both across time, sampling at a certain rate to update, which has to do with our temporal resolution, and sampling at a certain depth in terms of quantity. You can only have so many different shades of gray. So let's discuss scan conversion specifically. Remember that the endpoint is a stored image. Now our typical stored image is rectangular and made of rows and columns of square or rectangular dots. Each of these dots is called a pixel, or picture element. And each of these picture elements is a specific shade of gray. But what's our starting point? Our starting point is a continuously varying voltage that the transducer is sending us. One big string of voltages per line of the image. So remember, if we graph that voltage first time for each of those lines, that would be our A mode image. And in a big way, the first part of scan conversion is stringing those A mode images together. And what that means is we need to get a digital signal out of analog voltages. And the part of the scan converter that does this is called an analog to digital converter. Realize that when we're converting this three ways. We're converting it across time. That continuously varying signal across time is being sampled into small chunks, which determines our temporal resolution, how fast we're recycling all this. It's also broken into chunks based on space. We don't look at infinitely small spaces, we look at spaces the size of a pixel, whatever that is for the settings you're using. And finally, we digitize across contrast. We don't use every single value for voltage. We use a specific number of values that we can store in our pixel. I want to reiterate those points. When we convert from analog to digital, we're converting in three ways. The first is temporal. The converter needs to update fast enough for us to have a realistic image. In our speedometer example earlier, a speedometer that only updates every 2 minutes isn't going to give you a great idea of how fast you're going at any given point in time. Similarly, for our ultrasound image, we need to update fast enough that we get a coherent image. Usually, we describe this in terms of frame rate. We also need to digitize spatially. Each portion of that voltage correlates to a pixel. A pixel is not infinitely small, so we convert this using the range equation, which you should be able to recall from our previous lectures. Again, the time when the signal arrives correlates to how far away the signal is, and using that we can calculate precisely where in space we're converting from, and then we can digitize that number. Finally, and most practically, we need to digitize contrast. We get a continuously varying voltage, and that voltage can be any number, but the brightness we display on the screen can only be one of as many shades as we can store. So we can store each of those points as a specific shade of gray, and we can code each of those shades of gray into a binary number, and that gives us how many shades of gray we're using. So how many shades of gray do we need to use? This is really the same question as asking how many bits are we going to use to store each pixel? Well, one common way is to use 1 byte. Remember, 1 byte is 8 bits. And remember, the amount that you can store in a given number of bits is 2 to the power of that number. Well, 2 to the power of 8 gives us 256 shades of gray that we can use. Another common unit of storage is 10 bits per pixel, which gives us 1024 shades of gray. Why do we need to use so many different shades? The human eye can actually only differentiate around 64 different shades of gray before it all really blends together. 64 shades is only 6 bits. So are we wasting our memory? Are we using too many bits to store things? No. And the reason is ambient lighting. Looking at a screen with bright spotlights behind you is very different from looking at a screen in complete darkness. And that number of shades of gray covers the ambient lighting difference and other factors that contribute to image quality differences and color differences that you would notice. Now, we've previously talked about contrast resolution with respect to the quality assurance lecture. Contrast resolution is a question of how many shades of gray you can display. How close in color can two objects be, and have you still be able to tell them apart? Now, there are aspects of this that you can't control that have to do with the probe and wear and tear, but there are aspects of this you can control in terms of machine design, and that is how many bits are in each pixel, which is what we talked about earlier. Again, with 8 bits, that's 1 byte, you can get 256 different shades of gray, and with 10 bits, you can get 1024 shades of gray. Those are the two most common, and if you just memorize those two numbers, you'll probably be okay for the ARDMS exam. However, remembering the general case, that it's the number of bits, 2 to the power of the number of bits, that gives you the number of shades of gray. That would be ideal.